Just 1 second to share. Um, uh, uh, Good morning, everyone. Welcome and thank you for joining me. My name is Ali, and I'm excited to present my research on multi-project scheduling with limited preemptions and ordinary feeding precedence relations. So, um, to start with, our industrial partner produces customizable clean rooms, and these clean rooms are tailored to meet specific preferences of the clients. The production process is managed in modules. Each undergoes the same workflow until the final installation. This ensures consistency, quality, and efficiency in satisfying the client's requirement. And here on photos, we see an example of the main product of our client, our industrial partner. Our industrial partner receives requests for fabrication of clean rooms, and these requests can be negotiated, cancelled, or adjusted later, meaning orders are only started into production after approval. And estimating the necessary work of a project is a planning key step. Several estimation methods exist, including point estimation, commonly used in agile project management. And this method assigns points to each task based on its relative complexity compared to other tasks. The total points provide an estimate of the work needed to complete the project, as it's shown here. And despite this uncertainty, our industrial partner uses an Excel file to plan all the projects to allow them having a medium-term view of resource utilization, evaluate their capacity to accept more requests, calculate their manufacturing costs, and make strategic decisions regarding subcontracting, outsourcing, or hiring. Uh, okay. Um, So we took a look to the literature, and we can distinguish two ways to see the problem. The first is like to consider multi-project scheduling as scheduling of one big project, integrating all single projects. And the other is to consider each project independently with its corresponding objective function. As for the preemption, we can realize preemption through different modes. For example, the first is to split an activity into continuous sub-activities, or by allocating discontinuously the distribution of the energy, and govern then the scheduling of these activities with the precedence relations that we classify into four big classes. We start with ordinary precedence relations, defining minimum and maximum time lags. Then the ordinary feeding precedence relations, where we condition the starting of an activity based on the work that we achieved on the previous activity, which our case here. Generalized ordinary precedence relations, which defines a relation between initial and final part of two subsequent activities. And then we group all these properties all together to get the generalized feeding precedence relation. For the kind of relations that we are interested in, we have four possible settings in the literature. We are using the first one labeled as A, where G activities start only after achieving minimal ratio of activity of the previous one. I here. Coming to the position in comparison to the literature, we picked two references to base our work on that we selected from a set of articles based on features like multi-project setting, preemption, precedence relations, and the data that we are going to test our formulation with. We set ourselves a main target, which is to deliver a mathematical formulation that promotes for exact solution, preemption, overlapping, and respecting the minimum progression ratio of previous activities. We extracted them the sub goals, divided it to 3 sub goals, and we started by aggregating the operational activities into more generic activities, which are machinery, welding, paintwork, finishing, that are scheduled alongside with 2 other steps, which are sketching and design. Then again, for the mathematical modeling, we set ourselves to minimize delays and make span, and then we branched our formulation and research based on the preemption mode. So on the left, we have the continuous activity splitting, and on the right, we have the discontinuous energy allocation. We highlighted in green the main adaptation that we led for the different formulation to meet our industrial partner expectations. Coming to the parameters of control, we first present this flow chart, and we should notice that during the 2 first activities we have non-material stock, so we allow preemption. For the finishing, that is the final step that we are considering in this scheduling, also we allow preemptions to promote for managing varying complexity, while we restrict these preemptions in the intermediate activities, as operational activities require that there is no stock there. For overlapping, it's allowed only between sketching and design from one side, and design and machinery from the other side. For the formulation A, as we split the activity into sub-activities that are continuous and they continue for 2 weeks to get satisfied, we also have a constraint that we cannot suspend the work before epsilon weeks of continuous work. And for formulation B, we control the number of preemptions by controlling the periods of inactivity, while on the formulation A, it's controlled directly by the number of sub-activities. For the experiments, we constructed 3 different portfolios with different sizes, and we calculated the accumulated workload in main day. We tested those portfolios with different with the formulation A and B, and with combination of 2 different formulations of the objective function, OF1 and OF2. We set also 3 levels of limits of preemptions by activity, 0, 1, and 2. 0 to say like we realized we satisfied the activity without preemption. 2 to allow for 2 preemption at maximum. On the graph, we see the evolution of the workload energy needed to satisfy all the project included in the portfolio, and we compare all of it to the overall data that were given by our industrial partner. As for the instances, we solved like 324 problems to meet optimality using Cplex and a machine of 32 gigabytes RAM. Here in the table, we showed the significance of various features on solving time. Key points include the number of projects in the portfolio significantly impacts solving time more than workload. Formulation B outperforms Formulation A due to the better problem relaxation, and limiting preemption during the finishing has the greatest impact on solving time among sketching, design, and finishing. Here also we can see it showing the number of solved problems and the percentage. So we see again that B shows better relaxation than formulation A, while if we compare the formulation of the objective function 1 and 2, 1 seems better for formulation A, while it's the inverse for formulation B. Now in this graph, we considered like the 50, only the 15 project portfolio, and the average solving time for the 4 linear programming models, means combining formulation A or B with the objective function OF1 or OF2 with different values of MS, MD, and MF. The key points here are formulation A solving time increases with higher values of MS, MD, and MF regardless of the objective function. Also, the formulation B is less sensitive to these values due to the constant count of binary variables. And for formulation B also, it achieves shorter solving time and is more efficient as proved in the previous table. Overall, the formulation B with OF2 is a good compromise for utility, solving time, and sensitivity to preemption parameters. Coming now to the point of efficiency of both formulation to distribute energy, we have this graph that is shown the scheduling of the same project using the OF2 with formulation B and A. Here we can see when activities require small amount of energy, formulation A forces them to be scheduled at different times, even if they are doable simultaneously. In contrast, formulation B allows for concurrent scheduling here, making it more efficient. Coming to the conclusion, we recall that our project scope was to assist our industrial partner in having a tool promoting flexibility and agility for medium term and on generic point of view of decision. So we afforded 2 different mathematical formulation for it, allowing for the variance in intensity of work. As limitation, we saw that formulation A is less efficient to use portions of weeks and increased complexity of solving. For possible extension, it's possible to integrate decision maker preferences. That's why we use the mathematical formulation for an exact solution, which allows us to pull other candidate solutions from the feasible domain by taking another optimal solution or near optimal solutions that fits more to the decisions the decision maker preferences. And it's also important to promote monitoring to allow what-if analysis and facilitate the transmission of the instruction between levels of decision. Thanks and welcome for any question. Okay, so as I said earlier, our industrial partner used to use an Excel file to plan for its common projects. And due to the uncertainty that we have with the clients canceling orders or adjusting them, we don't know how much workload that we have exactly, and there is also deviation from what it's been estimated, and the performance of the teams progressing on the current projects. So basically, it's not straightforward to use an Excel file to plan all these projects, and also to calculate in a precise way the cost of these projects, and make also strategic decision about outsourcing and call or hiring extra workers. Also, it's less sensitive to holidays or day offs of workers. So we had to have a tool that at least it can assist the decision on a generic level. So this is the first point. Also, it's a part of total vision to implement a tool that makes it possible for the decision maker to negotiate with the solver that gives the optimal solution. Maybe the decision maker, he finds this solution is optimal, but it does not fit to his preferences, as he has special relations with some particular client, and he wants to adjust it for its priority. So we had to deliver a mathematical formulation, having the linear program form. Yeah. Well.